Good day, class. In the previous video, we learned what is a relative extrema. We also learned that using the first derivative of our function f, we can get what we call the critical numbers of f, and also the times when the function is increasing or decreasing. In this video, we will combine our results to obtain a test to find out whether a critical number is a relative extrema or not. Now, without further ado, let us begin. Now, recall that the main goal is to find the relative extrema of my function. And we have learned in the previous video that we can reduce the number of things to test by finding the critical numbers of my function. However, as was also said in the previous video, a critical number is not necessarily an x-coordinate of a relative extremum point. Now, this next theorem will help us test whether a critical number is an extrema or not, and that is called the first derivative test for relative extrema. Let us state it. If I have a function f that is continuous on the open interval ab, which contains a number c, and also suppose that f is differentiable on the interval ab except possibly c. So what this means is that you have continuity and differentiability both on the open interval. The only difference is that you are assured that you are continuous at c, but you are not sure if you are differentiable at c. This is a very important assumption, especially the assumption of continuity. One of the greatest weaknesses of this theorem is that we can only apply this theorem for continuous functions. If in case the function is not continuous, we will need to analyze more, as we cannot strictly apply the following theorem. The theorem states that since you are differentiable on the interval ab except at c, if you are positive, the derivative is positive from a to c, and you are negative at c to b. What this means is that the function is increasing from a to c and you are decreasing from c to b. Continuity means that it will coincide at the point c. It concludes that you will have a relative maximum because you increased and then decreased. Similarly, if you have a negative from a to c and the derivative is positive from c to b, it means you decreased first and then increased later. This means that you have a relative minimum. And if the sign does not change from a to c to b, then that means you have no relative extremum. Now, things to note here are the following. One, this is a very beautiful theorem, as it always gives us a conclusion. That is, it tells us whether you have a relative max, a relative min, or you don't have a relative max or min at all. Number two, you can only apply the first derivative test if you have a c, this number c. And this c is essentially a critical point. So instead of analyzing every real number in the domain, we will obtain critical point c and analyze what happens on the derivative at the left of c and on the right of c. Third, the first derivative test also affirms the fact that a relative extremum of a continuous function is a change, is a point of change. That is, you will have a relative extremum if the derivative changed at that point c from positive to negative or from negative to positive. It also means that you are a relative extremum of a continuous function if there is a change in increasing or decreasing, from increasing to decreasing and decreasing to increasing. The important parts here are as follows. Number one, you need to be assured that the function is continuous. Number two, you have a critical point c to analyze. And number three, you know the derivative and you can find the signs of your derivative. Now let us try to find relative extrema of f using the first derivative test. Here are some suggested steps in finding it using the first derivative test. Number 1, we need to find the derivative of f. In some cases, we already give the derivative of f for clarity. However, be assured that if you are going to be doing this from the bottom up, a wrong derivative means everything will be wrong. Remember, if the derivative is wrong, then the critical number is wrong. The signs of the derivative will be wrong, and thus all the conclusions will most probably wrong as well. So the most important step is actually the first step. You need to get the derivative well. After getting the derivative, you solve for the critical numbers, that is, the values that will make the derivative 0 or non-existent, and then I will construct a table of signs. Remember, I told you before that the critical numbers have this synergy with the sign by the intermediate value theorem applied on the derivative. If the function is continuous, then a change of sign will only happen when either you are at 0 or when it is non-existent. And then after that, we are just going to conclude by the first derivative test. Let us demonstrate that through the following example. I have f of x equal to x to the fourth plus 2x cubed. Let's first get its derivative, which is 4x cubed plus 6x squared. Now remember this, since we are on the application side, we don't just blindly differentiate. What does this mean? When you have a function and you have a derivative, there are forms that conform with different parts of the solution. For example, it is very easy to differentiate a sum. However, in finding critical numbers and the signs of my derivative, always remember that it is the factored form of your derivative that is important. That is the factored form 2x squared plus 2x plus 3. That is, you want that the governing operation will be either multiplication or division, because it's easier to see when it is plus, positive, or minus when you have these operations governing your quantity. For example, because you have already factored it, it's easy to see that the zeros will be the zeros of individual factors, 0 and negative 3/2. Also, to get the sign negative plus plus, we can just use test value method, and that is, you get a number less than negative 3/2, and that will be negative 2, and then you plug it on the individual factors. Negative 2 squared is positive. That will mean that this factor will give you a positive sign. Negative 2 times 2 plus 3 is a negative, so plus times minus will be minus. That will be much easier than evaluating negative 2 at x cubed and then subtract and adding it to the evaluation at 6x squared, which will be much time consuming. It's very easy to evaluate the quantities on linear factors such as x squared and such as x and 2x plus 3. Of course, you can just continue. For example, to get the sign plus here, I just get a number between negative 3/2 and 0, which is negative 1. Negative 1 squared will be positive, so that this becomes a positive number. 2 times negative 1 plus 3 is a positive number, and thus giving you the positive. You can also get plus here similarly. And what you obtain will be a table of signs. That means you are increasing from negative 3/2 to positive infinity, continuously closed, because you are positive on the open interval here. You are decreasing on negative infinity to negative 3/2. You can actually also place a closed bracket here, but this is also correct. And because you have a negative to plus here, so you have decreasing to increasing, you have a relative minimum at x equal to negative 3/2, while no relative extrema at 0, because you did not change from plus to plus. You will see here that the conclusion is actually the easiest part of the solution, the main trick for this item is to factor it well, because from the factors you can easily get the zeros and the signs by doing test value method. Let's have another example. I have f of x equal to x squared over 9 minus x squared. Similarly, I will get the derivative of this. Notice that to differentiate this, I will use quotient rule. And when you use quotient rule, it will become very complicated. But, of course, you can simplify it and you'll be able to obtain the following quantity. Notice it is very important that you simplify your quantity into something of this form where the governing operations will be division and multiplication. We can also easily see that the derivative will be 0 at 0 and it will be undefined at 3, negative 3. However, if we are being asked what the critical numbers are, surprisingly, we only have a single critical number. Remember, a critical number has two main properties. Number one is that its derivative will be either 0 or undefined. But it has also another property, which is that it should be in the domain. Unlike in the previous item, where it's a polynomial and the domain is all real, you need to be always vigilant that in cases of this, since this will not be defined at 3 and negative 3, even though it's undefined at f prime, it is not a critical number. This is a very important step because remember, you are choosing relative extremas on your critical numbers. So, removing the plus minus 3 there means that you will not have the chance to conclude that plus minus 3 will be a relative extrema, or f will have a relative extrema on these points. However, when you make table of signs, you still include negative 3 and 3. A good question is why? It is because of the intermediate value theorem. Remember, a very important assumption here is continuity. So we included 3 and negative 3 here, not because this quantity is undefined, but rather because f prime is discontinuous at 3 and negative 3. So because of the discontinuity, you will include it. So in a table of signs, you include not only the zeros of f prime, but also the numbers that will make f prime discontinuous. And that's evident here. If you evaluate, it will become minus minus plus plus. And then, concluding, you will be increasing on 0 to 3 and on 3 to positive infinity. Notice, I cannot place a inclusive bracket for 3 here because at 3 you will be undefined. Same thing for the decreasing. I need to cut it at negative infinity to negative 3 and negative 3 to 0 because I cannot include negative 3, even though you are decreasing for the whole open interval. Because for you to be able to include the endpoint, you should be continuous, but you are not because f is undefined at these points. And we can now conclude that you have a relative minimum at 0 because you go from decreasing to increasing. Now, a helpful tip when you have the following will be to understand some behavior of your quantities. For example, a nice tip here will be as follows. Remember, one of the important parts of the solution will be finding the signs. And we learned that these lines here, the undefineds as well as the zeros, are points of change, points of possible change. That means the signs can change or it can also not change. So how do you know that something changes? Well, the one good observation will be as follows. You will notice what contributed 0. It was contributed by the factor x. What contributed negative 3? It is contributed by the factor of 9 minus x squared, which is 3 plus x. And 3 is contributed by the factor of 9 minus x squared, which is 3 minus x. You will see that there was a change at 0, but no change at negative 3 and 3. The reason why is because of the square. Since the power of x here is an odd power, there is almost an assurance that there will be a change in the sign, because it is the only one giving you the 0 as a critical number. And similarly, negative 3 and 3 will not give you a change in sign because of the square. That is easily seen because when you evaluate things left of negative 3 and right of negative 3, there will be no change because the square will always make it positive. Of course, these are just simple tips that we can use, but the best way to do this is to just try to evaluate and check truly if you are negative or positive on the interval. Now let's have one last example. Now I have the function which is equal to negative x to the 4/3 plus 4x to the 1/3. Similarly, I will differentiate it. Now, though the derivative given in the slide is quite beautiful, but in truth, the derivative of this is negative 4/3 x to the 1/3 plus 4/3 x to the negative 2/3. It is actually not in factored form. So what you need to do there is to place in the denominator those with negative exponents and then factor it out, and thus giving you the 4/3 here. You factored out 2/3 in the denominator, and interestingly enough, you will have a factor of x minus 1 in the numerator. This is not as easy as it looks like, so it's a good exercise that you do this at home and try to find out how I was able to go from the derivative of f to this factored form. But since we already have the factored form, it's a matter of getting the critical numbers. So the question is, how many critical numbers do we have? F prime is 0 at 1 by this factor, and it is undefined at 0 by this factor here. So how many critical numbers do we have? The answer lies from the domain of f. The domain of f is all real. That means we include both 0 and 1 as my critical numbers, unlike the one before. So it doesn't mean that you have a 0 or 0 as in the denominator or undefined derivative, is that it is not a critical number. It's a case-to-case basis. You always check the domain whether the 0 of the numerator or the 0 of the denominator will be a critical number. You do the same as well, and you will see here that you will have signs plus, plus, minus. Going back with what I have taught you before, what contributed 1 is x minus 1, whose exponent is an odd number, while what contributed 0 is x squared over 3. So because of the square, it did not have a change in sign, and you will notice that you are increasing from negative infinity to 1. We included 0 because it's part of the domain. Decreasing from negative 1 to infinity. Notice, in this case, I wrote both brackets. This is still correct. And you will have a maximum here because you increased first and then decreased later. And that is how you got the answer for this one. You will not have a relative extremum at 0 because there was no change. Now in total, the theory for finding relative extrema is very easy. To get it, we first get the critical numbers. It will narrow down the number of things that I will need to test, after which I will use the first derivative test so that on each of the critical numbers, so that I will know which of the critical numbers are relative extrema or not. A very classic mistake here is that sometimes we are lazy, that after getting critical numbers, we stop. But notice here that the critical number step is a very short step. So in this case, if you have an exam and you did not write the first derivative test, then we'll actually miss a lot of points because finding critical numbers is truly not enough for you to get the relative extrema. So always remember, there will always be two parts, the critical numbers and the test. And that's how you get relative extrema. Now I hope you learned well in this video. Stay safe and thank you for watching.